Okay, so let's see how this works. So we have our function f of z. If I can have your attention, please, ladies and gentlemen at the back. Thank you very much. Yes, I'm looking at you. Thank you. So we have two series expansion, which we have in products with different indices, as I've discussed before the break. So on one hand, we have the series expansion for the complex exponential, which goes something like this. And we multiply it with a different series expansion, stressing that this is a different index. We have z to the power of n, which is a series expansion of 1 over 1 minus z. And of course, we can simplify this just bringing everything together as a summation over m and n, z to the power of m plus n divided by m factorial. Now, if you're not convinced, you can transform this like this. This is valid. A good thing that you can always do if you're dealing with series expansion is just write it down explicitly term by term, not for an infinite number of terms, obviously, but only pick like 2 or 3 terms, and then you can easily convince yourself that you're actually allowed to do this. And just to give a little bit more of a different perspective of how to handle products of series, I will do something very trivially simple, perhaps insulting to your intelligence, but let's still do it. And let's take the product of two very simple series consisting of 2 terms each, right? And then after thinking extremely hard and working hard, you know that you can write this as follows, right? So this was a very difficult task, okay? But what you see, of course, if you have a product of 2 terms with another 2 terms, you end up with 4 terms. And what I would like to do is write that down, is depict this in sort of a graphical way. If we depict, for example, on the horizontal axis, the indices corresponding to the first series, to the A, so let's say that this is then 1 and this is then 2. And here we have the indices corresponding to B, we have 1 and we have 2. Then you can see that we have these 4 terms that we can associate these 4 terms with 4 different points in this plane covering these 2 indices, right? So this just illustrates that if you have a product of 2 with another 2 terms, that you have 4 terms. If, on the other hand, you have, as we have here, the product of an infinite number of terms with an index going from 0 to infinity, so if we have here, for example, m and then there n, then we have infinite times infinite number of terms, and that we can depict by making sure that we have all of these crosses, right, and so on and so forth. So having a product of series expansions means that you need to sum all of the contributions from all of these individual crosses here, and you need to add them up together. If you have 4 terms, that was quite simple. It's only these 4 guys that you needed to sum. But if you have a product of real infinite series expansions, you need to make sure that you sum the contributions from all of the crosses in that diagram. Now, there are many ways you can walk through this diagram and be sure that you capture all of the crosses, that you don't forget any of these crosses. You could, for example, say, I'm first going to look at m equal to 0 and then add all of the contributions for n varying from 0 to infinity. I then look at m equal to 1, and I look at those guys, and so on and so forth. Or rather than doing it like this, you could also do it horizontally or any way you want. But the important part here is that you need to find a way to make sure that you don't forget any of these crosses in this diagram, because otherwise you run into trouble and you don't get the correct results. This can also illustrate that you would run into trouble if you had the same index here in your summation. If you had both m and also m for the 2 different series expansions, that would mean that rather than summing all of these points here, you would only sum the contributions along the diagonal, where the 2 indices are the same. So by artificially imposing the fact that these 2 indices should be the same, you make a mistake, and you omit, like most of the important contributions, you only sum those from the diagonal and not the off-diagonal elements. So this is just a different way of looking at these summations of the products of these 2 series expansions. Now, going back to the actual example that we're interested in, I told you we needed to transform this, z to the power of m plus n, in such a way that we have an explicit formula for the coefficients of a certain power of z. And here we don't have a single well-defined certain power of z. We have z to the power of m plus n, and m plus n run around independently. So this is not yet the final form that we're after. What do we need to do? We need to do, of course, the following. We need to replace m plus n by k, and then coming up with the coefficients of z to the power of k, right? Okay. Now, if we introduce here now an artificial dependency between m and n by introducing the variable k, this also has some consequences in how we walk through this diagram here. Since it's becoming quite messy here, let me redraw the diagram. So we have the m indices and the n indices, and we have all the different crosses here, so we should not forget any of these crosses. Let's now look at where the k values are in this diagram. So first, where is k equal to 0? That only happens when m and n is equal to 0, so this is this contribution. K equal to 1, you have either m equal to 1 and n equals 0, or the other way around. So these are the 2 points corresponding to k equal 1. This was k equal 0. You see a pattern emerging. This is k equal 2, and so on and so forth. So by making the transformation from m plus n to k, you see that you now have a different way of making sure that you don't forget any crosses in this diagram, but rather than doing it horizontally or vertically as we did earlier, now you do it diagonally. But as long as you don't forget anything, that's fine. This also tells you, okay, if you want to have all of the points covered in the diagram, k is running from 0 to infinity. You see that quite clearly. In order to capture everything, k needs to run all the way to the top right, so k equal to infinity. If you have, for a given k, and let's say, for example, m for a given k runs from, just look at the diagram. So let's look, for example, here, k equal to 2. What are the values of m that you have along this line? Well, you start by m equal to 1, 0, 1, 2. So for k equals to 2, m runs from 0 to 2, and more in general, for a general k, m runs from 0 to k. So m has taken on a slightly different role compared to what we started out from, because here in the very beginning, in the early days, m was a summation index completely independent from n, and both of them ran from 0 to infinity, independently of each other. Now what we've done by introducing this relationship m plus n equal to k, we've introduced an we've introduced a dependency between m and n. They're no longer independent, but they are linked through k, and that also has consequences in terms of their limits. You see, in order to cover this entire diagram, if you say that k is the independent variable, if k runs from 0 to infinity, for a given k, m only runs from 0 to k in this case. Is this roughly clear how this transformation occurs and what the consequences are in terms of the limits of m? So this is just by using a graphical approach. I kind of like graphical approaches, but okay, sometimes you have people which are more in favor of algebraical approaches, so let's also do a more algebraical explanation of how these limits change. Although I have to add immediately that this algebraical picture sometimes does not give you the full story, so you have to be a bit careful, but it's just a different way of getting to the same result in this particular case. So if we do the substitution m plus n equal to k, knowing, of course, that both m and n are positive values in our limits of the original series expansions, right? If we then look at n, for example, we haven't talked about n yet in this diagram. N is, of course, after a very complicated calculation, equal to k minus m. And we know that n is positive. If we know that m is positive, that means that now, in our case, then m cannot be bigger than k. So simply by this more algebraical approach, you can also get the same transformation of limits. So just to put everything together then, we can write down for our series expansion, we had this minus sign which was still floating around. We cover all the points in our diagram by first having a summation from k running from 0 to infinity. And that gives us all terms which have the same power, namely z to the power of k. And the coefficient of z to the power of k is itself a series expansion. It's coming from running along this diagonal here. And the coefficient explicitly is a summation of m going from 0 to k. And then you just look at what you're left with here. Where do I have my expression? The only thing that's left with is this factorial, the summation of 1 over m factorial. So this is the explicit formulation of the coefficients of a certain power of k. Is this clear, this approach? This is perhaps a different way of looking at the product of series expansions compared to what you might have had in the past. But I kind of like this graphical approach. Now for fun, what I suggest you to do, it's a little bit more difficult, is also look at the series expansion of this particular function for the outer region, namely z bigger than 1. That will give you a good opportunity to practice all of these transformations again with indices. And later on, in later chapters of the course, we will encounter these products of series expansions again. So it's a useful trick to know. Okay. If there are no more questions about our friend de Laurent series, then let's talk about something completely different now. And that's having an inventory of all the singularities in the complex plane that functions can have. So I've used this name before already in a quite loosely defined context, so now we will talk about this in a little bit more detail. And essentially singularities are there questions at the back? No questions. Singularities are points where the function is not well behaved or does something funny, and we will see that in the complex plane there are different types of singularities than the ones that you're used from in real analysis. So let's start looking at the zoo of singularities, and the first ones that we're encountering are the so-called poles. Apologies to people from Poland in case they're present. But how do we classify the poles? Well, we make use of our newly found Laurent series expressions. So I've told you what we did was earlier making the Laurent series around the origin. If we now have a singularity at a point z0, we can center the Laurent series at z0, and then simply we have an expression like this. So this is a more general expression of a function evaluated around the singularity at z0. Now in the most general case, m, the summation index, can run from minus infinity to plus infinity, but not all of the terms of the series expansion need to be present explicitly. So let's say, for example, that the series expansion does not start at minus infinity, but rather starts at a lower bound minus m0, for example. So let's look at a number of cases. Let's say that the lower bound is minus 1, so m0 is 1. If the lower bound is minus 1, then what we have is a pole of order 0. People at the back, I'm having trouble with my throat. I'm trying my best to speak up that everybody can understand me. It's very annoying for me if there's people talking all of the time through each other, okay? So I would appreciate it really if you concentrate and not talk through while I'm talking. Thank you. Okay. So if the lower bound is minus 1, we have what's called a pole of order 1. A pole of order 1, or also called a single pole. Pole that's not married yet, right? So an example could be f of z is of course a very trivial example, 1 over z. The series expansion, the Laurent series expansion in this case, is quite trivial, the function itself, 1 over z. So you clearly see that this only starts at 1 over z. That's a single pole. If you have lower bounds minus m0, then you have a pole of order m. So you could have, for example, f of z is 1 over z squared, that's a pole of order 2, and so on and so forth. So this is nothing special, but it becomes a little bit more interesting if you have the case where the lower bound is minus infinity. So if all of the terms going all the way to minus infinity are present, then we have what's called an essential singularity. And this is something a bit special. An essential singularity is also an example of a function where you cannot get rid of the singularity by multiplying it, for example, with a polynomial. In these cases, you could get rid of the singularity by multiplying it with z squared, and then you had a nicely well-behaved function. If you have an essential singularity, there's no way you can multiply it with a single polynomial and get rid of it. It stays there, so that's why the name essential comes from. So the classical example of an essential singularity is an exponential, not of z, but of 1 over z. So we can quite clearly, easily write down the series expansion. The series expansion, we had it earlier, it's a summation from m0 to infinity, 1 over m factorial, and this time it's not z to the power of m, but rather 1 over z to the power of m. And you clearly see that this contains negative powers of z all the way to z minus infinity if you want. So there's no way you can get rid of the singularity by multiplying it with a polynomial. There's something funny about essential singularities in the complex plane, and that is that their limit is not really defined. Depends very much again on the direction of approach. That's something you could prove. We're not going to do that. And also something quite funny is that, excuse me, if you have, like in this case, the essential singularity at the origin of the function exponential 1 over z, and you take like a very small region around that essential singularity, as small as you want, with an epsilon neighborhood, then you can prove that even within this tiny region, the function takes on all possible complex values. So that also shows you that the limit really cannot be defined. So essential singularities are really quite funky, and they don't have a counterpart in real analysis. Okay, these were the poles. So we just get them by looking at the Laurent series and then classifying them depending on the orders of the negative powers of z that you have. Questions on the poles? If not, we go to something more exotic, something which you do not encounter in real values analysis. And these are singularities called branch points and branch cuts. If you look into Dutch textbooks, they're called vertakkingspunten and vertakkingslijnen. And they're a bit difficult to understand. Well, difficult to understand it, so it's of course, I'll try to do my best to explain it as well as possible. But you need to follow along quite carefully. If at one point during my explanation you lose me, just don't hesitate to interrupt me and ask any questions. But I'll try to introduce it step by step, what all of these things are about. So let's take it easy and start by looking at a real function. A simple real function that you've encountered before, y is equal to the square root of x, which is of course the inverse function of x equal y squared, right? But you've been so used to looking at expressions like these that perhaps you forget that this is not the full story, that actually there are two solutions to the inverse problem that we have here, namely the positive square root, but also the negative square root. You have minus the square root of x and positive the square root of x. So if we draw this in a diagram, like this, we have the positive branch, square root of x, but you also have the negative branch, minus the square root of x. And you see that you really need both of them to get the full picture here, because they together form the parabola, which is the parabola described by the function of which you take its inverse. So both of them are important to get the full picture. So the function y equal the square root of x is actually a multi-valued function. So there are two answers to the question, like what is the square root of 4? It's +2 and -2. But humans, and especially computers, they don't like to deal with ambiguity. So if you have your calculator and you type 4 and you hit the square root button, obviously you want a single answer to make your life easier, and also life of people designing calculators or computers. So this is why people traditionally restrict themselves to just looking at the positive root. So you make this multi-valued square root function, you make it single valued by restricting your choice to positive answers. So y is bigger than 0. So I hope that I haven't told anything world shattering here. This should be quite familiar to you from a long time ago, I hope. But it serves as a springboard to now looking at what's happening in the complex plane. Because in the complex plane, something similar is going on. If we look at our newly acquired friend, which is the complex square roots. Now, in order to distinguish the real valued square root from the complex square root, we have a rather funky way of writing this down, namely z to the power of 1/2. This is just notation, I can't help it. In the complex plane, people prefer to use this notation for z to the power of 1/2 as a square root. Now again, this is the inverse of the function, of the square function, right? So if w is z to the power of 1/2, then z is w squared. And also here, we have two solutions present. We have a solution z. If we start from z, you know that you calculate square roots. That's very easy to do that if you have the polar form of a complex number. So if you have z and you want to calculate the square root of z, w, well, one solution, w1, is given by the square root of the modulus. Since rho is a real number, we can safely use the root sign again. So this is a real valued square root that you all know and love from a long time ago. And you divide the arguments by 2, the angle. So you have exponential j theta over 2. This is one solution. There's of course a second solution, which is minus this solution. But perhaps to illustrate where this minus sign comes from in a slightly different way, you can say, okay, this is z rho exponential j theta. There's nothing that forbids me to add to add 2 pi to that argument, right? Exponential j theta plus 2 pi. Because if I have an angle and I keep on adding 2 pi, nothing happens. It's exactly the same angle. However, if I follow the recipe of calculating square roots of complex numbers, I have the square root of the modulus, and I take my argument and I divide it by 2. I have exponential j theta over 2 multiplied by exponential j pi. Exponential j pi is -1. So this is another way of explaining where this -1 comes from, where this multi-valuedness comes from. It essentially comes from the fact that the angles, the arguments, they're not defined up to multiples of 2 pi. And if you then plainly use the recipes that you have for calculating square roots, namely dividing the argument by 2, of course, if you add 2 pi, it doesn't matter, but if you add pi, then of course the argument changes. So this is another way of looking at the source of this ambiguity. And of course, w2 is minus w1. So this is nothing different compared to what we had here with these two branches. So let's follow the same reasoning as we did for real valued square roots. What we would now like to do is obviously make a drawing of the complex square root. That's a bit of a problem because, of course, this is a 4-dimensional beast, right? So z, the argument, has a real part and an imaginary part. W, the result, same problem. So 4 dimensions. How are we going to represent a 4-dimensional object in such a way that we can look at it and inspect how it behaves? So I'm looking at you guys. Do you have any suggestions on how to depict a 4-dimensional object in like this two-dimensional space of the screen. How would you do that? Any creative suggestions? That's a possibility, but then you need for each point make these two plots again. So rather than just having two plots, you need like an infinite series of two plots. So it's a possibility, but you could then pick a number of interesting points. Is that unwieldy perhaps? Other suggestions? What's a technique you can do if you just make the problem a little bit easier? If you have a three-dimensional object and you want to plot it in 2 dimensions, how do you do that? You just add the third axis and then perspective, right? So there's a well-known way to plot three-dimensional objects on a plane. So we still need to add a fourth dimension. So how would you add a fourth dimension to like a three-dimensional plot which you projected x, y, z on a two-dimensional plane? How would you add a fourth dimension? Yes?
Perhaps with a color gradient.
Color code is a possibility. Perhaps somebody else has another suggestion. So one thing you could do. So you have a three-dimensional plot. So for example, you could here have the real part of z, the imaginary part of z, and then here you could plot the real parts of w of the results. So where do you go with the imaginary part of w? One suggestion was, of course, to use color for that point, and then use different colors for different values. Another thing you could do, which is perhaps not so practical for complex analysis, is to have the fourth dimension being represented by time. So just have a movie of something evolving. That's also a possibility. But in this case, let's stick with colors. This will tax my drawing skills to the limit. I already had problems with this resembling a square root function roughly. So this is why I need some help from a computer, if I still have my window open here. So here we have the representation of this complex square root function. This particular surface here has a name. It's called the Riemann surface. And we can play around with it. We can rotate it in all possible ways. You have the Maple worksheets which generate this also on the website of the course. So just to walk you through it, here we have W being equal to U plus I, in this case V. As we have a relationship between W and Z. Here we, just for technical reasons, take C to be the square root of W rather than the other way around. We have X and Y being the real parts of an imaginary part of Z. And then we plot, what do we plot? We plot X, Y, and U along 3 different axes. And then the important point here is that the color, we give each point a color related to the imaginary parts of the result, the imaginary part of W. And then you get something that looks like this. Now if you rotate it just to right, perhaps a bit like this, then you can see indeed that what's still present in this thing is this parabola here. Of course, the real valued square root should be contained within the complex square root, obviously, right? So that's good. But you see that it rather has a funny shape in the sense that it intersects itself. And you also can quite clearly see that I have some trouble rotating this back. Anyway, I hope you can see that for each value in the horizontal plane here given by X and Y, for each value of Z, you have 2 different values of W, of the square roots, namely one lying here, one with positive values of U, and also another result with negative values of U. There's of course one exception, and that's the origin here, because the square root of 0 is 0, and plus 0 and minus 0, that's of course exactly the same thing. But apart from that, for all of the other points, you have contributions from the positive parts here, from the higher branch, and from the negative parts here. So this is a double valued function. We can also have a slightly different representation, and that we can get by now not having color from the imaginary parts, but rather have color from theta, from the angle. If you have polar representation of the angle of the result, it gives you a bit more clearer sense of what's happening, especially what's happening if you take an excursion on this Riemann surface. So say, for example, let me rotate this slightly more differently. Let's see what happens if you start, for example, here in the green part, and you want to make an excursion over this Riemann surface, as it's called, of this square root. You walk around. What do? So you first, let's say you walk in the counterclockwise direction. You go from the green to the blue. You're still below the XY plane. But then here you cross over. You see that continuously you go from blue to purple here. You walk around like this. Here you're in the second solutions above the XY plane. The phase changes to yellow. And then you go down again from yellow to green. And then you're back where you started from. So if I walk around, if I do one excursion on this Riemann surface, how many times have I circled around the origin? Or what's the change of angle that I had when doing this excursion here? So if I project this path that I've been taking here and I project it on a single 2D plane, how many times did I circle around the origin? I see somebody raising 2 fingers, and indeed you circle around the origin twice, as you can see here. You do it once, so if you start here, you've circled around the origin once by the time you arrive here in the red zone, because the red point is directly above the green point where you started. And then you need to have another turn completed before you end up where you started from. So walking around the Riemann surface means having the angle changing by a factor of 4 pi, if you want. Right. So, following the same line of reasoning as we did for the real valued case, we have a multi-valued function. For each value of z, we have 2 possible values of w, one lying above the xy plane, one lying below the xy plane. We would like to have our computers give a single unambiguous answer, so we're going to restrict the solutions to just one of these 2 guys. And for example, we're going to choose that we're only going to look at solutions for which the real part of w is positive. So only solutions which are lying above the xy plane here. So this is the choice we're making here. So what that of course does is it rather destroys this beautiful structure of this Riemann surface. Perhaps let me go back to this thing once more. If you cut away the bottom parts, then you see that all of a sudden you have some sort of scar tissue, because of course previously on the full Riemann surface you were able to walk around and have a continuous change of color. But if you now throw away the bottom parts of this Riemann surface, you take your scissors, you cut this away, now you can clearly see that there's no longer a continuous change because you need to jump from this yellow to this purple region here. So you introduce some sort of issues, some sort of problems in the complex plane, and these are special types of singularities, and this is where this branch point thing comes from. So we will discuss this in a little bit more detail here. Are there at this stage any any questions about what I've discussed? Okay, let's continue. So let's write down our w plane and our z plane. So w is z to the power of 1/2, and z is of course w squared. So we're going to draw two complex planes, see how they relate to each other. And we've said for W, for the solutions, we're going to restrict ourselves to cases where the real part of W is positive. So only these guys we keep, real part of W positive, and those guys we throw away. Now, what are the implications for the Z-plane? Yeah. I don't have that much space here. But let's see, for example, this boundary between the good guys and the bad guys in the W plane. Where do we find the equivalent boundary in the Z plane? Well, the boundary is of course given by the real part of W being equal to 0, and that you can represent by W being equal to plus or minus AJ, right? So positive imaginary and negative imaginary parts. In the Z plane, that corresponds to W squared, and both of them map to minus A squared. So these two guys all map to this line. So this line maps to here, and also that line maps to here. So this is where the boundary occurs in the Z plane. So we go from Z to W. Z is the input of the complex square root, W is the output of the complex square root. And what I now want to show mathematically, again, just by the same result as we had from looking at the colored figures, is that if you go across this boundary line, so let's say from a point Z plus to Z minus, like this, and you evaluate the square root of Z plus, and you evaluate the square root of Z minus, we need to prove that they're not continuous, they jump. So this is what we're now going to prove, that if you move across this, what's called branch cut, you have a jump in your function is no longer continuous, and therefore that counts as a singularity. And by the way, the point where the branch cut originates, that's called the branch point. And in this case, that's given by the origin, which is a special point where the square root of 0 is equal to plus 0 or minus 0, so you don't have a change. Okay, let's evaluate the square roots of the point Z plus and the point Z minus. So what is Z plus? To evaluate square roots, it helps to look at polar representations. So Z plus is a point which has a certain radius, certain magnitude, and it has a certain angle, a certain phase. What is the phase? Well, of course, you know phase starts at 0 here and then increases like that. So this is how you count theta. So the phase for a point Z plus is not quite pi, but it's a little bit less than pi. So it's pi minus a certain small value, epsilon. And of course in the limit, epsilon will go to 0, right? So what is the square root of this particular point Z plus, given our restriction that we're only going to consider points for which the real value of W is positive? Well, let's first try the most obvious solution. So let's first try for W plus the square root of a rho exponential j pi over 2 minus epsilon over 2. Let's see where this ends up in the W plane. So it has a certain magnitude, square root of rho, but we don't care about that magnitude, right? We care about the phase. What is the phase? The phase is pi over 2, so that's 90 degrees, but it's a little bit less than 90 degrees. So this puts us somewhere here for this point W plus. Is this on the good part of the complex plane? Yes, this is indeed a point for which the real part of W is positive. So this is the one to keep. Its brother, minus W plus, would be lying somewhere over here, and that's not a good solution. That's not a choice we keep, that's one we throw away. Right? Now if we then take the limit of epsilon going towards 0, you see that this reduces to the square root of rho exponential j pi over 2, and exponential j pi over 2 of course is j. So this is j square root of rho. This is the result you get from a point lying just above your branch cut. Okay, everybody still happy? let's move to z minus, which is a point below our branch cuts. It has the same radius rho, and it has a phase, which is roughly pi, but this time the phase is a little bit higher than pi, so because we're lying below the branch cut. So, what is a possible solution? What would be w minus? Well, let's try the obvious thing first. Square root of rho exponential j pi over 2 plus epsilon over 2. Where does this point excuse me, where does this point w lie in the w plane? It has a certain angle, which is roughly pi over 2, but pi over 2 plus a small number. So this time we end up somewhere over here, and this is smack in the middle of the forbidden zone, so this is not a choice we're allowed to keep, so we should move to its brother or sister, and the w minus that we're after is actually minus the solution that we have, and this is lying in the correct half plane, so we should multiply this by -1. And if you then take the limit of epsilon going towards 0, you have w minus being equal to minus square root of rho j. So if you compare w plus with w minus, you see that indeed you pick up an extra factor of -1, which is an extra phase shift of pi, right? So here you clearly see that if you walk around in the z-plane and you keep track of what's happening in the w plane, you're still continuous as long as you walk here. But as soon as you cross the boundary here, as soon as you cross the branch cuts, then you jump from this point to this point, because you need to respect this choice that we imposed, and therefore you have a discontinuity. So this really is the nature of these branch cuts. So by itself, the complex square root does not suffer from any discontinuities. It's a beautiful function which is described by a Riemann surface where you can walk around in a continuous fashion. It's only because us silly humans want a single answer for this multi-valued function that we took our scissors and then brutally mutilated this beautiful complex Riemann surface. We cut away half of the Riemann surface, and then if you're restricted to walking around at the top Riemann sheet here, then of course you run into discontinuities, as you see here. So the branch cuts and branch points are not fundamentally associated with the square root itself, but they're a consequence of us wanting to force single valuedness on this function. Is this roughly clear, or is this still mysterious? So what I suggest really that you do is that when you come home, you read the first notes on this topic, that it sinks in a little bit more in detail, because sometimes it's easy to get confused between W's and Z's and what's really going on here. But at the end of the day, I hope that you will see the light and know where the branch cuts are coming from. Okay, so I've already used the term Riemann sheet. So because of the branch cut, the Riemann surface actually separates into two Riemann sheets. So for Z, we've actually said if we move open this branch cut a little bit so that it's clearly that they're consisting of two lines being separated, we have the Z plus guys lying here on the line A and the Z minus guys lying on the line B here. In this so-called Riemann sheet, we have that the argument of Z runs from minus pi to plus pi. So this is like sheet 1. So we start from minus pi at B and we run from pi to pi at A. But we should not forget that there's also a second sheet, sheet 2, also in the Z plane here, a second sheet. And we could say, symbolically, that since if you just look at the three-dimensional picture again, if you start from B and you run across here, A, you can still move continuously over to its counterpart of A in the second Riemann sheet. And then you can still increase the argument running from pi to 3 pi, for example, like this. and then you end up back at something which matches the B again from the first Riemann sheet. So if you want to like construct your own Riemann surface, you take two pieces of paper, you cut these lines, and then you find some way by going through hyperspace to join them in such a way that this A line here gets glued to that A line here, and then B gets glued to that B here. And then you have again your full Riemann surface made up out of two different Riemann sheets. Okay, let's talk a bit further about the implications of the existence of these branch cuts and these branch lines. So if you have your square root function, which has a branch cut here, oops, what I've done here is erased everything by accident. Obviously, what you cannot do, if you want to play around with our friends, Cauchy 1, 2, and 3, you cannot have a contour like this, right? Because that violates the fact that you cannot encounter singularities in your contour. Here you clearly have a singularity because you run into discontinuity. So, no way to do that. Like this, what you could do, for example, is again cheating a bit and having a contour which goes like this. That's perfectly fine. So you have your two line segments here again, L1 and L2. But in this case, L1 and L2 will not cancel because they're lying on opposite sides of the branch cut. So this is an example of a case where these two line segments don't cancel. So be aware of this in exercises that you don't say their contributions cancel each other. In this case, that's certainly not true. Another remark I want to make here is, yeah, you could say we have here the choice that we imposed the real part of W being positive. Why can't we choose the real part of W being negative? Or why can't we choose, for that matter, the imaginary part of W being positive? So, is there a special reason why we pick the real part of W being positive? Anybody thinks there's a special reason for that? Indeed, it's a purely arbitrary choice. You can even be funky and say, okay, I'm going to make rather than separating W plane in two by this line here, I will say, okay, perhaps I just draw this line and I will only keep these solutions. There's nothing that forbids me to do this. Or you can draw any funky line. If you're feeling really adventurous and you want to make your life very complicated, you can even draw a boundary that's not straight, that looks like this. So basically you have the full freedom to pick your choice of branch cuts, because remember, it's not inherently present in the square roots. It's just something that we humans impose to make the function single valued. The only restrictions on the choice of branch cut basically are that you want to make your function single valued, right, of course, so just pick one out of the different two solutions, which means that you cannot pick a branch cut that goes like this, for example, because then there would be still two solutions here present. So you should make your function single valued, and of course you also should take care that after you've identified the branch cut and calculated it back to the z-plane, that you can still walk around everywhere else and not cross the branch cut and still do so in a continuous fashion. But the branch cut choice is basically your own. However, I do want to add that sometimes there are some physical reasons why to pick a certain branch cut. And this comes, for example, and then we're talking photonics again, it's a while since we've talked about photonics. So what does this thing represent? I hope you've seen by now that this is a plane wave, something in the basic photonics courses. You also know that Kz, there's of course a Kx and a Ky present. And they have, sorry, this is wrong. So this also, there's also a square root involved here. So there's the magnitude of K in vacuum, and in order to calculate Kz from Kx and Ky, there's a relationship between these two guys, and there's a square root involved. Of Of course, you could pick the plus sign or the minus sign of that square root. And there you can have physical reasons dictating the choice of branch cut. Choice of branch cut is a pedantical way of saying the choice of picking plus or minus in the square root. Namely, you could have a case where you want to have a wave propagating either in the left direction or the right direction, or in case you have loss or evanescent waves, you want to have waves which decay exponentially rather than grow exponentially. So there could be physical reasons why to pick a certain sign, why to pick a certain branch point, a branch cut rather. And there could also be other examples where it's just easier for the exercise you're solving to pick a certain branch cut. Okay, there's a nice exercise associated with branch cuts, but given the timing and the fact that I'm losing my voice completely, I think we can postpone that to next week. So next week we'll do that exercise, but be sure to read up on this in the course notes, that you know very well what branch cuts are and branch points. And if there are any questions in the meantime, don't hesitate to contact me. Okay, thank you very much.